Nighty.
For project 1, our group decided to work through problem 3, which is as follows. You have a sled of mass m with a battery-powered snowblower that provides a thrust that decreases linearly from F0 at t equals 0 to 0 at t equals t, at which point the snowblower stops working. If the sled starts from rest on flat snow that has a small but non-zero coefficient of friction, what is the total amount of time the sled travels before it comes to rest again? From what we are given in the problem, we can make a few definite assumptions. We can ignore any effect air resistance may have on the sled as it travels. We know there is some amount of kinetic friction applied to the sled. We can assume that the battery-powered snowblower applies a horizontal force to the sled over time, and we can gather that there is zero vertical acceleration since the sled only travels in a horizontal motion. For our diagrams, we have a visual representation that shows how the thruster has the force decrease linearly from F0 to T. Then we have our free body diagram, which shows that the force of gravity and the normal force are equivalent in magnitude, and that there is a positive acceleration force pointing to the right due to the thruster. And then we have a velocity graph that shows
I guess you can just...
I don't know really how to describe that one.
Yeah, you can just say, and then we have our velocity graph.
Okay, and then there's the velocity graph. So in order to start solving the problem, we have our variables for mass, initial force, the coefficient of kinetic friction, the variable for time as a constant, and then the variable at which the snowblower stops working. We know that the initial velocity is 0, and we have the equation for the force of kinetic friction.
Okay, so next slide. Okay, the sled does not move in the y direction, so the y forces are in equilibrium. Therefore, the force of gravity will be equal to the normal force. Since we know what the force of gravity is, which can be seen by the equation F equals ma, where the sled's mass is just denoted by m and the acceleration is g, we know that the force of gravity is mg, and since the two are equal, the normal force will be mass times gravity. We are told that the snowblower provides a thrust starting at F0 as its magnitude, and it linearly decreases to 0 at t equals t. So knowing this, we can create a y equals mxb function where we know m, the slope, will be f0 divided by t, and b, the initial force, can just be represented as f0. And so we have our f thrust function, negative f0 over capital T multiplied by t plus f0. The net forces in the x direction can be found by finding the difference between f thrust and f of kinetic friction. So using the two equations that we found before, this gives us f in the x direction is negative f0 divided by capital T multiplied by t plus f0 subtracted by the coefficient of kinetic friction times mg. We can find the kinetic friction force by multiplying the coefficient of kinetic friction by the normal force. So using this equation, we can find that the force of kinetic friction is equal to the coefficient of kinetic friction multiplied by mass and gravity. Acceleration can be found by dividing force by mass. So dividing the force in the x direction by m, we get a new equation for acceleration. To find velocity, we take the integral of acceleration from t equals 0 to big T.
So by integrating from 0 to big T, we find the initial velocity after the snowblower finishes working. And after the snowblower finishes working, we can plug that into a new equation to the post-engine time. At which that point, the only force causing acceleration is just the friction now, which is negative mu k times g. And so we integrate that acceleration, we can integrate that in order to get velocity. We plug this into a new velocity equation in order to get the full velocity, which we can then solve. So by setting that entire equation to 0, we find a t value, which is equal to capital T times f0 over 2 times mass. But the important thing here is that t is only from when the snowblower cut out to when it stops. So in order to find the full thing, we also have to add the time that snowblower is on, which conveniently is just t. So we add capital T to that, and that gets us our final time of capital T times f naught over 2m plus capital T.
The unit should be in time because when you cancel all the other units that accompany the equations that gives us time, t would be the only thing left over. The coefficient of friction is small, meaning the time would be less than what the time would be if there was no friction. The sled is slowing down, meaning it would take less time to stop if there was nothing to stop it because it would just keep going on forever. The answer is reasonable given the equations that were used to solve this problem. We have done questions that were similar to this problem in our Top Hat written homework, studio and lectures, physics, my lab and mastering, and in our third lab. Although it differs because we usually only go as far as solving for the coefficient of friction, for this problem we had to keep going and solve for time using the coefficient of friction.